Hello and welcome to the presentation of our capstone project, Detection of Solar Plants on Satellite Imagery. Because of the massive buildup of solar systems within the last years in Germany, we as Versicherungskammer want to detect solar plants on satellite images based on any given address. This is because we want to perform targeted sales campaigns for solar plant insurances. We started with analyzing data sources such as ESA, NOAA, and Google Maps, and finally decided for Google Maps Static API because of the high image resolution, the easy collectabilities, and the simple address mapping. These images we had to label. We modified an existing labeling tool for our purposes to be as efficient as possible.
So before we start training the network, we have to pre-process the images, and we use the Keras image data generator. This creates more training data by rotating and shifting images slightly. As you can see, the orange outline shows the original image, and it was rotated and shifted. We also use the image data generator to normalize all color channels, which helps in training the network. This is the network we used. It's a convolutional neural network with 4 convolutions and 1 final fully connected layer, which then gives us the final output of solar panel on the image or not. To evaluate our network, we used a saliency map, which highlights the areas in the image which contributed most to the image score.
Okay, coming to the results, we saw that the model performed quite well during the training. After about 50 to 60 epochs, we achieved 90% accuracy on the validation data. Afterwards, we saw slight overfitting, and those can be seen in the accuracy gain and loss decrease. So we decided to stop early at about 60 epochs and use the model here where no overfitting is present. We then validated the model using test data, which consisted of 950 images and a classification threshold of 0.75. So the model only classified an image as having a solar plant if it's at least 75% sure. We achieved with the model a precision of 94%, a recall of 81%, and a combined F1 score of 0.87. We can also see in this graph that we have to make some trade-offs between precision and recall. Of course, the higher the precision, the lower the recall. And we chose 0.75 as a threshold, as it still provides a high level of precision without strongly decreasing recall. So to conclude the project, solar plant detection using convolutional neural network definitely works. But we also quickly realized that labeling is a bottleneck and needs to be coordinated quite well. The approach and the model still pose some challenges. For example, the map static API provides quite heterogeneous spectral quality and sometimes imprecise address markers which do not sit directly on the house. The model also recognizes not only solar plants, but things like tree shadows, greenhouses, and maybe swimming pools. Also, the precision recall trade-off can be fine-tuned for the final application in which the model is used.
Let's come to the outlook. When labeling the images, we notice that sometimes there are several rules on images. Therefore, by using additional map services like the Zeus Geo or the Bayern Atlas, we could achieve better predictions. Then secondly, by using more diverse satellite imagery, we could build a more robust model. And first but not least, we had problems to distinguish between photovoltaic plants and solar term plants. So it would be good to find a way to distinguish between the both.
You can find a live demo of our project on solarplant.herokuapp.com, where you can predict the solar plant presence on any given address. Thank you very much.